Start recording. And let me share my screen. Apparently, I didn't open the question. Okay. Can you see this screen? I think
Yes,
you
Hocam.
can. Okay, let me stop sharing for a second. Close my cam. And then share again. Okay, I think you can see again the example one. This is a pump example. And there is a head loss, of course, in the solution as well. We cannot think both of them separately. Let me read the question, then we will talk about the solution. A water pump is used to pump water from one large reservoir to another large reservoir that is at a high elevation. The free surface of both reservoirs are exposed to the atmospheric pressure as sketched in the figure. The pump's performance is approximated by the expression H available is equal to H0 minus AQ square, where shutoff head is equal to H0, and that is 24.4 meters. Shutoff head means when the pump head when the discharge is 0. There is a value given for this A, which is 0.0678 meters per liters per minute square. This LPM means liters per minute, which is also written here. And what else? The question wants us to estimate the capacity, which is discharge delivered by the pump. The dimensions and minor loss coefficients are provided below. Also, density and the viscosity of the fluid is given to us. The elevation difference, the diameter of the pipe, the K values for entrance, valve, and the elbow is given. The total length of the pipe is given. And lastly, the roughness, pipe roughness is given to us. For the elbow part, you can see we have 1, 2, 3, 4, and 5 elbows. So we will multiply this value, this elbow K value, when we consider the elbow, the minor head loss coming from the elbows, because you know the formula is total K value. And we have this unit conversion given here for this LPM value. So 1 minute per LPM square means when you multiply it with 3.6 times 10 to the power 9, you'll get something like this. You don't understand what is this now, but when we solve and come to this stage, you will understand what I mean. This unit conversion is needed. This is why I put this conversion here. You will see. So we can start by writing our energy equation between the points 1 and 2. And let me close my window because cats are here. I think you can hear the sound. Okay, let's continue. When we write the energy equation between point 1 and 2, what do we have? We have the total at that point 1 minus the major head loss minus the minor head loss plus the pump head will be equal to the total at that point 2. So it will be something like this. This is total at point 1. Major head loss, minor head loss, pump head will be equal to total at that point 2. So what is the total at that point 1? Of course, the pressure head, velocity head, and the elevation head. Same for point 2 as well. Pressure head, velocity head, and the elevation head. We know these are large reservoirs, and you can see they are open to the atmosphere. So we can assume, not assume, it's a fact actually, we can say the pressure heads at point 1 and 2 are 0. Also, their elevation heads are 0. So what do we left with? We're left with only the elevation head, head losses, pump head, and the elevation at that point 2. We know the equation of major head loss is FL squared divided by T times 2G. L is the total pipe length with velocity. This is the pipe diameter, and this is the gravitational acceleration. And we also know the equation of the minor head loss as well. Total K value, V squared over 2G. So you will bring these two and put it into this equation, and we will get something like this. We'll keep it as it is for now. Then we will start putting values, of course. First, I calculated the total K value because I will need it. So what are they? For the entrance, we had 0. These are given by the questions I just showed you. Entrance, we have 0.5. For the wall, we have 17.5. For the exit, we have 1.45. And lastly, for the elbows, the value was 0.92, but as I said, we had 5 elbows. So we are multiplying this value with 5 and we get 4.6. When you sum them all, like I did here, you'll get 23.65. What is our next step? The next step is, of course, to put the values, what we know, into this equation. So what do we know? We know this difference given like here. Just let me remind you again. This is given, pipe diameter is given, we calculated, we know L, and that is all. Let's put them into our equation. So this is the elevation difference. This is the total length of the pipe diameter. We don't know the velocity, and we know the gravitational acceleration, which is 9.81 meters per second. Okay, and this is K value, again 2G. So when you do these calculations, because I want to simplify this equation, so basically I do this calculation and I do this calculation, and at the end we get pump head will be equal to 10.85 plus 443.15 FV squared plus 1.205 V squared. We will call this system equation because it comes from the energy equation. And if you remember the question, we had another equation related to pump head given us by the question. We will call this pump equation. It was H available is equal to H0 minus AQ squared. H0 and A was given to us, so we can put them directly into this equation. What was H0? It was 24.4 meters. And what was A? A was this much, something like this. And now I will show you this unit conversion here. So I wrote this pump head equation by given the question, H0 and A. And we know I told you here, 1 meters per liter per minute square was equal to 3.6 times 10 to the power 9 second square over meter to the 5. So I replace, actually not replace, multiply this value with this one, and at the end, for the A, we get 24,408 10 to the minus 10 to the 4 second square per meter to the 5. We got this one. This is our A. I just did a unit conversion. And I put these two into equation, h0 given to us and a value. And what do we get at the end? We get this one. So what do we don't know here? We don't know F value. We don't know discharge value. So this is a common type 2 problem. What do we do when it is a type 2? Basically, we start calculating this one, relative roughness. We assume completely rough flow. We leave velocity or discharge, it's about what is asked to you, alone. And while using this assumption, assume that value, you put it here, you find velocity, you go for iteration. I will show you how. First of all, you need to calculate the Reynolds number. Then you find the final F value, like here, and check if these two are close enough to stop. If they are close enough, stop. If not, go for the next iteration, and it continues like this. So in our example, we have one system equation for pump head, and we have one pump equation given from the question, by the question. So when we solve them together, because these are this one and this one, both of them are equal to the pump head. So they're basically equal to each other. When we equate them each other, we can find the operating point for our discharge value. So when you equate them, this is this one, and that is the one coming from the other equation. At the end, you need to leave V alone. So I take them into V square parentheses, the terms which have the V square. We have 25.55 plus 1.20 and 443.15 F will be equal to 24.4 minus this 7.85. And we don't want it in terms of square. We want to have it like only V. So I throw this as a denominator to here because we want V alone. Then take the square root, and at the end we get this equation for the velocity. So what do we need to do? As I explained, this is a type 2 problem, so we will assume completely rough flow. You know, our full equation is this one, but when we assume rough flow, we just cancel this one and we end up with this one. From here, we will calculate our initial F and we'll continue like this. So what do we need to calculate our initial F? We need relative roughness, which is epsilon divided by the pipe diameter. So we know epsilon is given us here as 0.25 millimeters, which is 0.25 times 10 to the minus 3 meters, and pipe diameter is given us 2.03 centimeters. So you'll multiply this by, or you can say divide by 100 to get meters. These are just unit conversions, and I did them here. Here you can see my unit conversions, and you do this equation, the calculation, epsilon over d, and this is our relative roughness. Now we can just put it here and find our initial F value, which is, I did here, you can see, is equal to 0.041. So once you get this F value, you'll just put it into here, and you'll get a velocity. When you put the 0.041 into this equation, we get 0.607 meters per second. So when you get velocity, you can calculate Reynolds number because we know this is density, this is velocity, pipe diameter, and viscosity of the fluid. These are all given us by the questions. I don't want to keep going up. I showed in the first place. These are all given, this density, viscosity, and diameter. We just needed the velocity and we calculated here. When you put it into equation, you can find your Reynolds number, which is 12,273.91. So by using this Reynolds number, you can either use Moody chart or this equation. It's up to you. It doesn't matter which method you use. You can calculate our final F value. So when you put this Reynolds number into this complete equation right here, your F value is equal to 0.0455. There is a bit difference, so it means we need at least one more iteration. So what is the next step? You take this F value and accept as your initial F this time, bring it here, and for this F, and you will repeat the same process. Take this F, put it into this velocity equation, get your velocity. For this much velocity, calculate your Reynolds number, and for your Reynolds number, use this equation or Moody chart and calculate your final F value, which is 0.0456. It's still a bit different, but it's very close. I mean, it's like 1/4 digit after the decimal. It's not that important. So it's very close. We can stop here. So we can accept this velocity as our operating velocity, which is 0.593 meters per second. The question was asking us the discharge delivered. So by using this velocity, we will calculate the discharge. How? It's very simple. We know discharge is equal to velocity times the cross-section area of the pipe, which is shown as A. So what is the cross-section area? P d square over 4. So what was the d? D is the pipe diameter given by the question. And when you do this calculation, at the end we get 1.92 times 10 to the minus 4 meter cube per second. If you want to convert it into liters per minute, from meter cube to liter, you need to multiply with 1,000. And from second to minute, again, you need to multiply with 60. And this is the final answer for this question. So if you have anything to ask, you can ask me now.
Hocam, I have.
Yes, what is your question?
First Fi, we can assume it, right? We don't have to use the equation for it.
As far as I know, you can assume, but it is better to use this equation. It will make you reach this step easier for you. And actually, for when you assume completely rough pipe, actually you need to calculate this relative roughness and put it into this equation. You shouldn't assume for this question when you assume as a rough pipe. Just assume completely rough pipe, calculate this relative roughness and put it into the equation. Do it that way. Anything else?
Hujam, how many elbows do we have in the question?
How many what?
Elbows.
5 elbows. We have 5 elbows. Let me show you.
Shouldn't we, Hujam, include the one going out from the pump?
No. It's just a sketch. We don't count them. The question doesn't count this one.
Oh, so
We have 1, 2, 3, 4, and 5. Don't like when I saw the question first, I thought like how you thought. I thought we had 6 elbows, but the question doesn't count this one. So we have 5.
Okay, yeah.
Any other question?
Yes, why did we choose the second velocity, not the first one?
What do you mean? You mean the second type of problem? Why
No. 0.5, not the first one that we
you
found.
mean why did we choose this one?
Yes.
Okay, this is a we don't know the velocity. Okay, when we reach this point, I mean, when we get this equation for the velocity, we don't know what is the velocity, and we don't know F value as well. It is not given by the question. So let me show you again. So we have different types of problems, okay? When we have some certain unknowns. For this question, the question asks us the discharge. And when we don't know the discharge and F value and the discharge is asked, it comes down to type 2 problems, okay? So when you have type 2 problem, the process you need to follow is, first of all, you will calculate this relative roughness. You will assume completely rough flow, and you will put into, actually, this is our original formula, but when we assume completely rough flow, we cancel this part, we don't see it, so it turns into this form. You put in this relative roughness into put into this equation, calculate an initial value, okay? So this is our initial F, but we don't know if this is correct. For this much F, to see, we need to carry this iteration. You take this initial F and put it into this equation to find the initial velocity. You find this velocity, but still we don't know if this is our operating point, because in the first place, we assume it's a completely rough flow and we cancel this part. We are trying to see if it is correct or not. So once you find this velocity, you put into this equation and find the Reynolds number. The point is why we are doing this iterations, because we want to use this original formula, okay, to see if our assumption was correct or not. So we need Reynolds number. After velocity, you can calculate it, and you can put this Reynolds number into this equation and find your actual F value for this velocity. Okay, our initial F value was 0.41, but our final, after we use the original formula, we get this much F value. So we say, okay, we found this velocity, but we got different F values after carried out this iteration. So this velocity is not our operating point. We need to continue. What is the next step? You take this final F value from here and accept as your initial velocity this time. And you put this F value again, this equation. You repeat the same process. You get the velocity value by using this equation. It is this much, okay? Again, we need to check if this F value is correct. So we need Reynolds number for that. We calculate it, put it into this equation. How do we calculate Reynolds number? By using this formula. Density, viscosity, and diameter given. We just needed velocity and we calculate it here. Put into this equation, find your final F value. They are still not exactly same, but this is the number, the fourth number after the decimal point. So it is very, very close. So it is acceptable. So we say, okay, this was our actual velocity, and this is why we are using this one. I took a bit long time to explain it, but I wanted to make it very clear. So I hope it's okay now. Any other question?
Hocam, will you upload this to the class, these solutions?
I might, but first I need to ask Hasan Hoca, because you know he's the instructor. So I will do whatever he wants me to do. Is everybody okay now about this question? If you have any questions, please ask. Okay, then let me stop sharing. So this was the first question. Now we will take a 10 minutes break, or do you want 5? Doesn't matter to me actually. Yeah, let's make it 10 minutes. 10 minutes break. I will see you after 10 minutes. We will continue with the second example. Mohammed, do you want to ask anything? Okay.